Have you ever, just look up and seen a glider? They just kind of float there, silently cutting through the air, no engine, no noise. It's kind of mesmerizing. And it makes you wonder how in the world they actually stay up there.
Yeah, it's a question we get a lot, actually.
Of course, of course. So you sent in some, well, really fascinating stuff, questions about how these engineless aircraft actually work. And we've been digging deep, preparing for today's deep dive into glider aerodynamics.
Lots of aha moments coming up.
Oh, yeah, tons of those. So we're basing this directly on what you shared, including, that really detailed GFHI AFH-3.pdf document and some really solid background info from the pilot's handbook. We're going to try to, distill it down, find the most crucial and maybe the most captivating aspects of how these engineless aircraft manage to fly.
Well, and to really understand, like, the essence of it, to get that moment, you have to kind of visualize how a glider moves, how it, pivots around its center.
Okay, so you're talking about like its movement in 3 dimensions.
Exactly. So imagine it like this. There are these three axes, right, all passing through the glider, intersecting at a single point, and these axes define how it moves.
Okay, so like a 3D coordinate system.
Yeah, pretty much. So first you have the vertical axis, that's yaw. That's what is the nose moving side to side, controlled by those rudder pedals.
Got it.
Then we have the lateral axis. This one runs wingtip to wingtip. And movement around that is pitch, the nose going up or down using the elevator.
Right, right.
And lastly, we have the longitudinal axis, that's nose to tail. And rotation around this one is roll, which the ailerons control.
Okay, so yaw, pitch, roll, those are the 3 basic movements, and they all hinge on this one crucial point where they intersect.
Absolutely. At that point, that's the center of gravity, or CG.
Ah, the CG. Everything kind of balances on that, right?
Totally. The CG is basically the point where the glider's weight is perfectly, balanced. And as you said, that balance is crucial for stable flight. It's like, think about balancing, say, a pencil on your fingertip. There's that one spot where it'll just sit there perfectly balanced. It's essentially its center of gravity. But for a glider, it's in 3 dimensions, not just one.
Okay, makes sense. So let's say our glider is up in the air, no engine, just gliding. What are the main forces acting on it at that point?
Okay, so when we talk about unpowered flight, the kind of pure gliding experience, there are 3 big players. First, you have lift. That's the upward force, fighting against gravity, the thing that's actually keeping the glider airborne.
Right, lift. It's kind of the whole point, isn't it?
Exactly. Then there's drag. That's the resistance the glider feels as it moves through the air, kind of like air friction.
Always working against you.
Always. And then, of course, we can't forget weight. That's the constant pull of gravity, always acting downwards.
Yeah, weight, good old gravity, always there.
Exactly. Now, if we were talking about self-launching gliders, the ones with an engine, we'd also have to consider thrust, the force from that engine. But since we're focusing on the pure gliding experience, it's those first 3 that are really doing the heavy lifting, so to speak.
Okay, perfect. So let's break it down, starting with, I guess, the star of the show, lift. How does this thing, without an engine pushing it forward, how does it generate that upward force, that lift? It seems like magic.
It does seem like magic, but it's really like elegant physics at play. There are 2 main principles that explain lift, and they actually work together beautifully.
Okay, lay it on me.
All right, so first we have Newton's third law of motion. Remember that one from physics class? But every action, there's an equal and opposite reaction. Well, think about the wing, right, slicing through the air. It's pushing that air downwards.
Okay, yeah.
So Newton's third law tells us that as the wing forces air down, the air pushes back up on the wing. That upward push, that's lift.
So a downward push creates an upward rush. That makes sense, kind of a direct way to think about it.
Yeah, very intuitive. But there's another piece to the puzzle, and that's Bernoulli's principle. This principle says that as the speed of a fluid, like air, increases, its pressure decreases.
Okay, so faster air, lower pressure.
Exactly. And here's where the shape of the wing, the airfoil, comes in. The upper surface of a glider wing is usually more curved than the lower surface. And because of this shape, the air flowing over the top has to travel a longer distance in the same amount of time as the air flowing underneath.
Right, it has to speed up to cover that extra distance.
Exactly. And as it speeds up, the pressure on top of the wing decreases, creating a pressure difference between the top and bottom surfaces. This pressure difference with higher pressure underneath results in a net upward force, which again is lift.
So it's both things working together, deflect air down, and that pressure difference. Pretty cool.
It really is.
Now, in the stuff you sent, I saw a formula for lift, something like L equals 1/2 RO V squared SCL. It looks, well, pretty complicated.
Yeah, it's a bit of alphabet soup at first glance, but it's actually not too bad once we break it down. So that formula is just a way to quantify, to put numbers to the lift we've been talking about.
All right, let's decode it.
Okay, so L, obviously that's lift. Rho, the Greek letter R, that represents air density. And it's important because, thinner air at higher altitudes means less lift, even if you have the same airspeed and wing setup.
Makes sense.
V is the velocity, the airspeed of the glider, and notice it's squared in the formula. That means even a small change in airspeed can have a big impact on lift.
So speed is really important.
Hugely important. Then we have S, which is the wing's surface area, basically how big the wing is. And lastly, CL, which is the coefficient of lift.
Okay, coefficient of lift, that sounds like how effective the wing is at doing its job.
You got it. It's a number that basically tells us how much lift the wing generates at a given angle. And here's where it gets really interesting for a pilot. This coefficient is directly tied to the angle of attack, or AOA.
Okay, angle of attack. Now, remind me what exactly that refers to.
So picture this. You have the wing, and there's an imaginary straight line drawn from the leading edge to the trailing edge. That's the chord line. The angle of attack is the angle between that chord line and the relative wind, the direction the air is flowing over the wing. As the AOA increases, the coefficient of lift usually increases, but only up to a point. It's pretty linear, actually.
And what happens when you push it too far beyond that point?
Well, you reach the critical angle of attack. If the nose is too high or the airspeed gets too low, the smooth airflow over the top of the wing, it starts to detach and get all turbulent.
Ah, so the air gets messed up.
Exactly. And when that happens, lift decreases really suddenly. That's a stall. It's something every pilot needs to be aware of constantly.
So too little angle of attack, not enough lift. Too much, you lose it. There's a sweet spot in there.
You got it.
And you also mentioned that lift is proportional to the square of the airspeed. So if you go twice as fast, you get 4 times the lift.
Yeah, pretty much. That's why maintaining the right airspeed is absolutely crucial in a glider. It's how you stay airborne. And really importantly, it helps you avoid stalls, especially during critical parts of the flight, like landing.
Now, one last thing about lift. The material mentioned that the center of lift is usually a bit behind the CG. Why is that?
That's because it creates a natural tendency for the glider to pitch nose down, to want to dive. Imagine those forces not being perfectly aligned. To counter this, the horizontal stabilizer on the tail has to generate a downward force to balance things out. This balancing act is what gives the glider longitudinal stability, which is its ability to kind of naturally return to its original pitch after being disturbed.
Okay, so the lift itself creates this nose-down tendency that the tail has to manage. It's a bit of a balancing act.
It is, definitely.
All right, so that's lift, the force pushing us up. Now let's talk about the force that's, well, trying to hold us back. Drag.
Drag, that's the aerodynamic resistance, the thing working against the glider's motion. And it can be split into 2 main types, parasite drag and induced drag. The total drag the glider feels is just these 2 added together.
Okay, 2 types of drag. Let's start with parasite drag. That sounds like something you'd want to, get rid of.
You definitely want to minimize it, and that's exactly what glider designers spend a lot of time doing. So parasite drag is basically the resistance from any part of the glider that doesn't directly contribute to lift. Think of it as the price you pay for pushing the glider through the air.
Okay, like air resistance.
Yeah, exactly. And it has a few components. You have skin friction, which is literally the friction between the air and the glider's surface.
Okay, so a smoother surface means less friction, less drag.
Exactly. Then there's form drag, which has to do with the glider's shape. A sleek, streamlined shape like you see in gliders offers less resistance compared to, say, a boxy shape.
Right.
And finally, there's interference drag, which comes from how the air flows, where different parts of the glider meet, like where the wings connect to the fuselage.
Okay, so where things join together, that can create more drag.
It can, yeah. Now, the really important thing to remember about parasite drag is how it changes with speed.
So the faster you go, the more drag.
Exactly. It increases with the square of the airspeed, actually. So just like with lift, if you double your speed, your parasite drag doesn't just double, it quadruples.
Wow, that's a big increase.
It is, and that's why glider designers put so much effort into minimizing parasite drag, especially on the wings and fuselage. That's how they get those amazing glide ratios. But it's always a factor, always something to consider.
Okay, that's parasite drag, the resistance from pushing through the air. What about induced drag? That sounds like it's caused by something else. Induced by something.
You're right on the money there. Induced drag is a byproduct of generating lift. It's caused by those swirling masses of air, the wingtip vortices.
Ah, those swirling things I've seen pictures of.
Exactly those. So as the wing creates lift, there's a pressure difference between the upper and lower surfaces, right? High pressure below, low pressure above.
Right.
Well, at the wingtips, the air wants to equalize that pressure. So it flows from the high pressure area underneath, around the tip, to the low pressure area on top, creating these rotating vortices.
So it's like the air is trying to cheat, taking a shortcut.
In a way, yeah.
And how do those vortices create drag?
Well, they effectively tilt the average direction of the airflow over the wing slightly downwards and backwards. Remember that lift acts perpendicular to the relative wind? So if the wind is tilted back, the lift vector gets tilted back too. And this backward component of the lift force, that's what we experience as induced drag. It's like some of our lift is being, well, induced to pull us backward.
So it's like a hidden cost of generating lift.
You could say that, yeah.
Now, how does the angle of attack play into induced drag?
Well, a higher angle of attack usually means the wing has to work harder to produce the lift we need, especially at lower airspeeds. And this extra effort leads to stronger wingtip vortices, a bigger tilt in the airflow, and thus more induced drag. It's most noticeable at those lower speeds. But on the flip side, as you fly faster, you need a lower AOA to get the same lift, which weakens those vortices and reduces induced drag.
Okay, so with speed, parasite drag goes up, but induced drag goes down. So is there like a sweet spot?
Absolutely, that's a really crucial concept. The total drag is just the sum of parasite and induced drag. And if you were to plot it against airspeed, you'd see this U-shaped curve. At the slower end, induced drag is the dominant force. As airspeed increases, induced drag goes down, but parasite drag starts to climb. And at the very bottom of that curve, that's where total drag is at its minimum. That's the airspeed where the glider achieves its maximum lift-to-drag ratio, or LDMX.
So that's the most efficient speed.
Exactly. Flying at that speed, you get the best glide and the most distance for the altitude you lose. It's a key piece of knowledge for any glider pilot looking to get the most out of their flight.
Absolutely. Now, the material also talked about this thing called ground effect. It sounds like, well, like the ground can help a glider in some way.
It does, particularly when you're flying very close to the ground, within about one wingspan's distance. What happens is, during takeoff and landing, the ground messes with those wingtip vortices. It disrupts their formation. And because of that, the downwash behind the wing is reduced, the vortices weaken, and you get a noticeable decrease in induced drag.
So near the ground, you get a little boost. It's like almost like the ground is giving you a little extra lift.
Yeah, you could think of it like that. And that's why a glider sometimes feels like it's floating just before touchdown.
Right, right.
And this reduction in induced drag during ground effect, it lets the glider take off at a slightly lower speed and extends that landing flare, making for a smoother touchdown. It's something pilots really feel.
Okay, so that's lift and drag. The third force we talked about was weight. That seems pretty straightforward.
It is, yeah. Weight is just the force of gravity on the glider's mass acting straight down through that important center of gravity. And in flight, the lift generated by the wings and the vertical part of any drag, they're working against this weight to keep the glider up.
And for level flight, lift has to equal weight.
Exactly.
Now, just to touch on thrust briefly, even though we're mainly talking about unpowered gliders.
Right. For pure gliders, that initial push to get airborne comes from something external, like a tow plane or a winch. Once the glider releases, it's all about converting potential energy, the altitude, into kinetic energy, the forward motion. And it does that through a controlled descent.
So it's a constant trade-off, altitude for distance.
Exactly. Now, power gliders, they have engines, so they can generate their own thrust, giving them more flexibility when soaring conditions aren't ideal.
Okay, so back to the unpowered glider, trading altitude for distance. How does that actually work in terms of the forces?
So imagine the glider is descending at a steady rate, not accelerating. The weight is still pulling it straight down. But because the glider's path is angled, we can think of that weight force as having two parts. One part pulls the glider forward along its path, like it's sliding down a float. Let's call that WF, the forward component of the weight.
Okay, so part of the weight is pulling it forward.
Right, and the other part acts perpendicular to the flight path, kind of pushing it down towards the path itself. That's WP, the perpendicular component of the weight.
Okay, and how do these two components relate to lift and drag?
Well, in a steady descent, everything is balanced. So the perpendicular component of weight, WP, is exactly balanced by the lift the wings are generating. And the forward component of weight, WF, that's balanced by the total drag force acting on the glider.
So in a way, gravity is the glider's engine, pulling it forward through that forward component of weight.
Exactly. That's how it moves forward without an engine. And a steeper glide angle would mean a larger forward component, right? So more pull from gravity and a faster descent.
Right, steeper angle, faster descent.
And at the same time, a steeper angle means a smaller perpendicular component of weight, so the wings need to generate less lift to balance things out. It's a constant conversion of potential energy, the height into kinetic energy, the forward motion.
That's the essence of gliding then.
It really is.
Okay, this constant exchange of altitude for distance brings us to the idea of glide ratio, which I know is a big deal for glider pilots.
It's a fundamental measure of performance, really. The glide ratio tells you how far forward a glider can travel for every unit of altitude it loses. And remember the LDMX, the maximum lift-to-drag ratio. Flying at the speed that gives you LD max, that's how you get the best glide ratio.
So it's all about finding that sweet spot.
It is, yeah. And a higher glide ratio is, of course, what you want. It lets you stay airborne longer, cover more ground, and that increases your chances of having a successful soaring flight.
Makes sense. So if someone says a glider has a glide ratio of, say, 50 to 1, what does that actually mean for the pilot?
It means that for every foot of altitude they lose, they can travel 50 feet forward. In still air, of course, assuming they're flying at that best glide speed.
So a glide ratio of 50 to 1 means you can glide 50 feet forward for every foot you descend.
Exactly.
Now, how does the shape of the wing design, play into this glide ratio? The material you shared mentioned different wing platforms.
Ah, yes. The platform, the basic shape of the wing, has a huge impact on both lift and drag, and therefore on the glide ratio. You see platforms like elliptical, rectangular, tapered, even some swept-forward designs, though those are less common. Each shape has its pros and cons, affecting how lift is spread across the wing and how much induced drag it creates.
So different shapes for different purposes.
Exactly. For instance, an elliptical wing, in theory, it gives you the most efficient lift distribution, minimizing induced drag. But it's also more complicated and thus more expensive to build, so there are always trade-offs.
And what about the aspect ratio? The material mentioned that gliders have high aspect ratios.
Aspect ratio, yeah, that's a key design element. It's basically the wingspan, the distance from tip to tip, divided by the average chord length, the width of the wing. Gliders, they're known for those long, slender wings, which means they have high aspect ratios.
Right, those long, elegant wings.
Exactly. And those wings are very efficient at producing lift, even at fairly low angles of attack, and they create less induced drag compared to shorter, stubbier wings.
So high aspect ratio, good for gliding.
Definitely. And you can actually see this in data, like in that figure 310 you mentioned. A higher aspect ratio translates directly into a better glide ratio. It's a fundamental principle of aircraft design.
Now, those little upturned fins you sometimes see on glider ring tips, the winglets, what are those for?
Winglets are pretty cool, actually. They're designed to make the glider even more efficient by tackling those pesky wingtip vortices head-on. They change the airflow at the wingtips, weakening those vortices, and that reduces induced drag. Basically, they make the wing act like it has a slightly larger wingspan without actually making the wing bigger, which would be more complicated structurally.
Smart. And another term that came up was washout. I think that means the wing is twisted slightly along its length.
Yeah, washout. It's a deliberate twist built into the wing. The root of the wing, the part closest to the fuselage, has a slightly higher angle of attack than the tip. And this little twist is actually a really important safety feature.
Okay, how so?
Well, if the glider gets close to a stall, the wing root will stall first because of that higher angle of attack. And that gives the pilot a warning, often a buffeting feeling.
Like a little shake.
Exactly. And importantly, because the wingtips are still producing lift, the pilot keeps some control over the roll, which is essential for recovering from a stall.
So it's all about giving the pilot more control, more time to react.
It is, yeah.
Okay, so all these design elements, the shape, the high aspect ratio, those wing lips, and that washout, they all work together to maximize lift, minimize drag, and make gliding safer and more efficient.
They do. It's a really impressive combination.
Now let's talk about how a glider stays under control. The material you shared had a section on stability. What are the different types of stability we need to think about here?
Okay, so stability in the context of flight refers to the glider's ability to naturally return to a balanced, stable flight attitude after being disturbed, like by a gust of wind or a pilot input. And we generally talk about two types, static stability and dynamic stability.
Okay, two types.
Yeah. So static stability, that's all about the initial reaction to being moved out of balance. Will it try to return to its original position? Will it move even further away?